afternoon, good evening, good morning indeed, if you're dialing in from those parts of the world. I'm Jarka Glassey. I'm the president of the European Federation of Chemical Engineering, EFCE, and I have taken on the role of the president in January this year, following 2 terms on the board of EFCE as the vice president executive. I'm actually a biochemical engineer by training. I graduated from the Slovak Technical University in Bratislava, but I worked all of my professional life as a professor at Newcastle University in the UK, recently taking an early retirement from there and engaging with other universities around the world a bit more. Whilst on the program you would have seen my colleague Wulos Hur was due to do the introductions. I'm afraid he's unable to join us today, but that gives me an opportunity to be involved in the introduction of this webinar on application of artificial intelligence to chemical reaction engineering and process intensification, which I'm really looking forward to because most of my work is actually around AI and machine learning, although in biochemical engineering, biopharmaceutical industry. So I'm really looking forward to this. Let me first say something about the Spotlight Talk series. This is now our 6th year of the Spotlight Talk initiative, which started in 2020 to keep together the community during the COVID pandemic. The success of the previous years convinced us to transform the Spotlights into a regular feature of the EFCE program. We have now 1 Spotlight series in every odd year and 2 in even years like this year. This spring, 11 of our working parties and sections are delivering over these 2 weeks 9 webinars of 3 or 4 talks focused on specific topics by leading industrial and academic experts. The series also enables attendees to sample matters in new areas, encouraging cross-fertilization of interest. And if you're interested, there are still some webinars upcoming, so you can check the complete program available on the EFCE website, and you will also be able to find recordings on our YouTube channel. Now a few words about EFCE. EFCE promotes scientific collaboration and supports the work of chemical engineers in 30 European countries, representing more than 100,000 chemical engineers in Europe. The working parties and the sections of the EFCE cover all major specific aspects of chemical engineering and are in fact at the core of the organization, forming the scientific engine that drives many of our activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. This year, I wanted to just bring up that EFCE introduced a new initiative, virtual coffee meetings with the president, so that we can discuss how we can strengthen our collaborations with colleagues. These coffees, I'm afraid, will be virtual and take place typically about 3rd Thursday of the month. And some of them are actually dedicated to member society representatives, and you would have gotten an email about that. But the others are open to anyone engaged with EFCE. And if you would like to pop in for a virtual coffee and a chat, please look at the website where you will find links to register for these events. I'm really looking forward to hearing from you. But before concluding, I would like to thank all the colleagues who worked hard within the working parties, sections and wider EFCE for this initiative to happen and to be successful. In particular, many thanks go to our Martine Pou in Toulouse. Thank you again, Martine, who did most of the conceptual setting up and practical activities. And now I'll just thank you for your attention and wish all the speakers and the attendees a fruitful and successful webinar. And I'll hand over the word to the chairs of the working parties of process intensification and chemical reaction engineering, Professors Stefanidis and Geem. Over to you.
Yes, thank you very much, Jarka. Good afternoon, everyone. My name is Georgios Stefanidis. I'm the chair of the EFCE Working Party on Processification and a member of the EFCE Working Party on Chemical Reaction Engineering. And on behalf of both parties, I would like to welcome all participants and speakers to today's EFCE Spotlight webinar. I'd also like to thank Wulos Hur, Jarka Glassey, Martine Pou for organizing and disseminating this event. The working party on PI, I'll say a few things about it. Our working party brings together experts from academia and industry across Europe with the aim of promoting and disseminating knowledge and processification, as well as advancing its role in research, education, and industrial practice. PI actually focuses on the development of innovative equipment, processing techniques, and operational strategies that can significantly improve resource efficiency, reduce plant size, enhance sustainability, and strengthen competitiveness of chemical processes. Today's webinar will focus on the application of artificial intelligence in chemical reaction engineering and processification, a topic that is highly relevant for both communities. As you know, AI has rapidly emerged as a powerful tool in chemical engineering, enabling new approaches for process design, for optimization, and operation, and for supporting more sustainable and efficient chemical manufacturing. In fact, our two working parties already organized a webinar on AI about 2 years ago. However, as most of you know, developments in this field are extremely rapid. The new methods and applications are emerging continuously. And for these reasons, it is important to revisit the topic regularly and provide updates to the community. The program today reflects this evolving landscape. We'll start with foundations for symbolic AI in engineering, followed by insights into domain-informed AI approaches in chemical engineering. Then move to agentic AI for next-generation chemical process design, and finally conclude with a broader perspective on the role of AI in process intensification. We're very pleased to host 4 distinguished speakers today who will guide us through these developments. Each presentation will last about 25 minutes, leaving a few minutes for questions. So please feel free to submit your questions in the chat during the talks. And with that, I would like to thank you all for joining us today. And I will now hand over to my colleague, Kevin van Him, the chair of the Working Party on Chemical Reaction Engineering.
Yeah, thank you, Georgios. So indeed, I'm the chair of the Working Party on Chemical Reaction Engineering of the European Federation of Chemical Engineering. This is a long-standing expert network dedicated to advancing the science and practice of chemical reaction engineering across academia, but also industry. We bring together leading researchers, practitioners, and innovators to exchange knowledge, stimulate collaboration, and shape the future of the direction of this field. We play a central role in organizing and supporting major international events. And I think most of you will know the International Symposium of Chemical Reaction Engineering, which dates back from 1957. And we also regularly contribute to topical scientific activities, webinars, the spotlight talks, and joint working sessions. Especially, we have now a strong focus not only on reactions, but also application of AI in this context, electrification of chemical process and process intensification, which shows why we do this together with the Process Intensification Working Party. Beyond the events, the Working Party facilitates community building. We recognize excellence through EFCE awards, and we foster the next generation of researchers. But I already talked too long. It's now time to start. And just one small correction. So for the people joining online, if you have questions, Martin instructed me to use the Q&A and not the chat. So please use the Q&A. Then and Georgios and I will pick questions when the speakers have finished. So you don't have to unmute yourself. We will take care of the questions. The speakers will try to answer the questions that have not been answered during the webinar itself, but they can answer in the Q&A section. And as it's supposed to be, the following introductions for the speakers are generated with AI, but double-checked. So I will start with Alexei Lapkin, and he's a professor of sustainable reaction engineering at the University of Cambridge, known for pioneering work in catalysis, process intensification, and digital molecular technologies. He studied chemistry at Novosibirsk State University and earned his PhD in chemical engineering from the University of Bath. His research integrates machine learning, AI, and life cycle assessment to develop more sustainable chemical process. He also leads an innovation center in digital molecular technology. Alexei, I think everybody looks forward to your talk, so the floor is yours, I would say.
Thank you. I just need to reshare. Apology for that. As always, it works much better in the... okay, this is very weird. Sorry, that system is confusing. I will reshare. Okay, yes. Okay, just check that you see in the right screen. Right? Okay. So thank you for the introduction and apology for the hiccup. I'm going to talk about the knowledge foundation for symbolic AI, and I will very quickly explain what I mean. This talk primarily based on the collaboration of two of my colleagues, Yizhe Zhang and Shuyan Zhang. They're not a family. Yizhe is now an assistant professor at the University of Manchester. Just to say thank you straight away for the people, I will talk about the work done by several PhD students and several master students who regularly come to us from Professor Mitzes in Aachen. It's also a collaboration with my colleague Markus Kraft and Lian Jiang in A-Star in Singapore. When we talk about chemistry, chemical processes, the domain of knowledge is very broad. We are talking about the scale, length scale, going from atoms to processes, and then above to flow sheets and industrial systems. In the time scale, we go from the reactants to products, then we make in the products that are typically phases. So what goes to the consumer is typically a mixture of molecules and phases. And in terms of sciences, it covers a very, very broad range of sciences. So of course, because of such complexity, it's a very difficult field, and introduction of tools helps us to bring a lot of this knowledge to experts. And AI, of course, helps to do this a little bit better. So my picture of the toolbox for digital chemistry is this. We have an experiment, whether this is a calculation or whether this is a lab, wet experiment or dry experiment. We try to automate those as much as possible. These generate data. Data needs to be machine readable and labeled and preferably semantically enriched with metadata. So we need a data ontology. Then this data is merged with all of the other chemical data which exists out there, whether those are commercial databases, ELNs, results from computational chemistry, mechanisms, thermodynamic properties, environmental impact. All of that is data. And preferably, we would like this data to be available, fair, labeled, and understood by the machines. We then use this data to understand the relationships and being able to formulate new hypotheses. And we either do this ourselves or we now use algorithms to do that. Once we've generated new hypotheses, we want to translate those into the new experimental formulation, and then that loop goes around. So I mentioned ontologies multiple times on this slide. So ontologies come from system science or from philosophy. It's a field in computer science. It's a very hot topic in tech at the moment, because ontologies is what makes language models accurate. So pretty much all tech companies are on the hunt for ontologies. In ontologies, you have classes, entities, relations, and axioms. And ontologies are not new to chemical engineering at all. This is a very well-developed field in chemical engineering. The biggest ontology we'll have is OntoCape. This is the product of the work of Marquardt in Aachen many years ago. It's a very, very large ontology. It's very heavy, very difficult to use and poorly annotated, but nevertheless, this is our common starting point. So what do we do with this, and why do I talk about ontologies? We can define ontological relationships about our molecules, about our species, about our processes. We can build the data and the relationship between the data based on ontologies into what is known as knowledge graph. If the knowledge graph is based on ontologies, it's actually correct. You can build a knowledge graph without ontologies, but then it will contain duplicates, erroneous connections, and it will not be very accurate. Once you have the knowledge graph, you can do all sorts of clever things in the agentic framework. So you can have pieces of code which interact with the knowledge graph, which then do anything you would like to do with the data, whether this is, and the knowledge graph can contain your raw data, it can contain specific experiments, it can be your equipment in a particular laboratory. So in principle, it's a very, very diverse system. So a typical scheme like this is also what you will see if you look at the conversations of the tech community about pretty much anything else. They'll have language models on the top, then they'll have the knowledge graph and ontologies below that. And that's pretty much what is being developed at the moment in parallel in tech and in domain knowledge as well. So specifically, I'm going to talk about two ontologies we've built recently, a model ontology and a process ontology. The model ontology is connecting the representation of the knowledge we have. So these are the formulas, the parameters of the formulas, the units, and we can build those now semi-automatically such that you can ingest pretty much the entire knowledge of chemistry, chemical engineering at this point, or you can expand it to any other domain. This is connected to the process ontology, where we have unit operations, streams, process variables, and that process ontology is then linked to a standard called DEXP, which then is a representation of the physical plant, and that allows us to connect to typical flow sheeting tools, whether they are conventional or whether they are AI-based. And the DEXP is a standard which most companies adhere to. So what do we do with this, and why we were building this for the last few years, and now we're finally publishing this? We use model ontology to automatically construct first principle models. We do this with the help of reasoning agents. Because this is ontology, we can reason with the ontology and assemble equations. We can then pass those equations to the simulation engines, and we can use these models in different practical scenarios. The primary application, what we were thinking about at the beginning of this work, is to scale the construction of digital twins. In the Industry 4.0, when there are fully digital factories, you need a digital twin for every widget on your plant. There are thousands of versions of similar devices. Each one of them will need to have a model. You cannot possibly do this by hand. It's too big a task. So some of this work needs to be automated to be scalable. So this platform we were building is basically for that, so that you can use AI codes to reason and construct correct models and calibrate them such that then digital twins can be generated very rapidly. So what's in that space? This is, again, the representation of the metagraph for the model ontology. It has the phenomena, which is the physical phenomena which is happening. This is the basic quantum. This stems from the work of Kai Sundmacher early on how to generalize process modeling through phenomena. This relates to laws, which are basically equations. The laws has variables and so on, and we link it to the digital identifiers. So you can find the papers or book chapters where the specific versions of these equations come from. This is then linked to the process matter graph. You can visualize how much data exists in a particular domain, and you can then see the connectivity of, let's say, specific variables to the laws and so on. So this is sort of visual work which you can then do with the knowledge graph. So what we do with this is, for example, we can do a bottom-up or top-down work. So the bottom-up is, you say, I have a particular unit operation. There is a generic mass accumulation equation. You set what are the flow patterns. You set what is the kinetic is. So you basically say, I have this type of kinetics. The model will pick up the relevant equations from the database and will assemble it into the correct version of the model. In the top-down approach, you can say, well, I don't know what's inside. I don't know what kind of kinetics is there. I know I have how many phases I have, what the temperature pressure is. So you give some descriptors of a process context, and we put this six-dimensional descriptor of the context. And then based on this context, our rule inference agents will hypothesize what are the possible models which fit to that context. We'll simulate all of them, or calibrate basically all of them, and then present the results and try to suggest which is the best version of this. Now, this paradigm runs in a way that the equations are treated in MathML. MathML is nice because you automatically can see it in HTML, so it's visualized correctly on screen. You also can then convert it, and we convert it into either Python to solve, or into Pyomo, or you can parse it into Julia. The output is a runnable code. And then, of course, because it is an ontology in a knowledge graph, this is AI ready. So you can use your favorite agents to work with. You can put a chat engine to communicate with this. You can build APIs to work with your favorite databases or favorite simulation packages, and so on. So let me show you an example. This is the one which is going to be, so the next two things are in the paper, which is accepted. It will appear soon, where we use the example of the axial flow reactor for making nanoparticles. It's quite complicated physics. The assembly of the final equation depends on the correct choice of the equations for the film thickness, for the actual equation for the flow velocity. You need to describe the chemistry and the mixing. And the chemistry here is the reaction which is typically used to characterize micromixing. These phenomena are selected. They are in a knowledge base. The code assembles the final equation and allows to simulate it. Once the model is calibrated, then you can visually see that, okay, results are pretty good. The parity plot is fine. And then it also allows you then to calculate. You can run simulations of the model. In this case, we're trying to get the mixing time correlation and then show, okay, actually mixing time is pretty good in this type of technology. So this is when we know what is the flow velocity equation. We know what should be we can pick the equation for the film thickness, and then we know the kinetics. So we basically use the engine to assemble everything together. In the other case, we use the example of the Taylor-Couette reactor. We had one in the lab from our collaborators, and they were running some tests, so we were generating data anyway. But in this case, we said, well, we don't actually know what the specific physics is valid for a particular range of conditions we were running. So we said, well, here is the context. This is the type of reactor. Just figure out what can be the correct equations and what could be the correct model. So there are multiple possibilities for the dispersion coefficient in this model for the axial dispersion. They all depend on your hydrodynamics. The hydrodynamics depends on how you operate this. And so it changes. You rotate the internal cylinder faster, you change the hydrodynamics, you change your dispersion coefficient equation. And so it will assemble all of these models, simulate them, and show how which one is the most likely out of the, in this case, it's simulated several models, and it shows that one of them is better than the other. And also, as you change the rotation, this choice of models will change. So this environment now works. We developed it to the point when we're now productizing it. So the code will be available as a software in this summer. And in parallel, we were working with two teams, the Cambridge team and the I2R team, to demonstrate how this environment actually works in practice. So this is part of the agents. So this ontology, the assembly of the models, then the physical model, these are all of the agents. These agents work with the GraphDB where the all of the knowledge base sits. It also works with the Postgres database and the MongoDB database, which saves the time series data. But that's your data side. That's all in the cloud. Through the connectivity, we had an intermediate server running in I2R, and that server was used to connect to the physical plant, which was a pilot plant run by our collaborating company. So this then becomes a full digital twin, and we spend time to solve all of the problems of data security, of how to run this communication, how to connect the physical plant with the edge server, and then with cloud compute. This paper is now published. All the codes of that, what we could release, are released. And anybody who is interested in building work in digital twins environment for industrial applications, at least this version of implementation is publicly available. So just to show a very simple case. So we had a more complex case described in the paper, but this is a feed module of a plant. I can't show you the plant, that's confidential, but the feed module is relatively straightforward. It has 4 tanks, it has multiple valves, and all of them the combination of those valves do different things. We use the model ontology, so tanks are in ontology, valves are in ontology, flow meters, reactors, it's all in ontology. We use the ontology to assemble the model and then to simulate and use it in the practical application. So this is what the model ontology does. There is a mass balance law, there is a mass accumulation law, there is a mass flow rate. All of those are assembled into a relatively simple model. I mean, the model here is very simple. It's just flow stuff into a tank. But that's not really a point. The point was to connect everything together and then use it in some applications of the digital twins. So we have 3 different types of operation. There is a Rins mode, there is a prime mode, and the actual reaction mode. Different types of valves and flows are connected in those. The model construction agent constructs all of those models and then simulates them. And then the simulation model is also linked with the deviation from the norm. And so how do we then use it once you have access to the full digital twin environment? In the full digital twin environment, we used this physics-based model for anomaly detection. Our colleagues in I2R built a data-driven model for anomaly detection, and we're using both of them together to see which one does better prediction for different types of different types of anomalies. And this can run either in the simulation mode, so you can have a simulator for testing so that it processes the data, combines with the data on the predictions, and then outputs the results, or it can run directly from the Kepware server, which is connected to the plant. So you can do it in real time. And this shows just the simulations. This is the physical model, how that predicts different types of faults, whether the tank is leaking or the flow rate region is offset or the valve is incorrectly labeled, and how the autoencoder AI model is doing similar tasks. So this is the piece which I wanted to show on how to create a workflow where if you have access to a knowledge graph, which is populated with physical understanding of reaction engineering, you can construct AI agents to work with this and create digital twins, use different agents to then do things like model calibration, model identification, create models, in this case, for anomaly detection in the real client environment. You can use this kind of models, and very briefly, I'll show this in the next couple of slides. I'm not going to go into that in too much detail. This is also recently published. You can use the same type of model ontology, but to generate different kinds of models. So in this case, we're looking at much more complex models where we may want to, for example, reveal the hydrodynamic model within the reactor system. That's the one I'm gonna show you as an example. And in this case, just using the reasoning agent may not be enough. You may want to do this as part of a reinforcement learning campaign. So for this, we've built this pipeline when we use the same ontology of phenomena. We then create compartmentalized models. We use another agent to create model equations. We then test them. We then solve them. We circulate this until we have the good solution, and then that ends up in a correct, hopefully a correct model. This environment is a little bit more complicated. It uses two Markov chain processes. It then uses cumulative reward functions from these two reinforcement learning models in order to design the equations for the processes. What is underneath of this? In order to build this type of processes, you need a way of manipulating equations, manipulating compartmental models. The technology for this already pre-existed, so we borrowed the idea of colored graphs, which are really convenient tool for manipulating process models, because you can add all of the things you need, such as different phenomena, connection of the surfaces of the blocks, as well as the actual compartments. And the output of this, for example, we wanted to develop a hydrodynamic model of the Taylor-Couillard reactor. The output of running this is this type of model, which shows what are the volumes there. It identifies that there is a block of PFR there is some kind of bypass inside, and so on. It basically gives us the residence time distribution type equation model. So this is the then slightly different application of the knowledge-based ontology in process reaction engineering. So my time is up. I'm going to stop here. Again, I'm going to say thanks to the team who was doing this work. But what I was trying to show you is the ontologies and development of connectivity to the fundamental knowledge, I think, is critical. It helps to create correct models. It will be these things can interact with language models of any kind, keep them within guards, and actually help to correct the solutions obtainable through the language models. You can build reasoning agents, you can build reinforcement learning frameworks on top, and make sure that you are on the right side of the reaction engineering, let's say, so you're not hallucinating in any way. So I'll stop here, and then that hopefully allows time for questions.
Thank you, Alexei. Thank you for this great talk. There's a first question from somebody anonymous. Who designs these models?
So
it's chemical engineers or software engineers, or a combination of both?
No, the physical models are designed by chemical engineers. In fact, we've tried to do the automated ingestion of this. It's not yet working very well, so we do it semi-manually. When we look at the fundamental equations in the literature, we then quantize them into phenomena. We have a particular way of writing those equations that they are always solvable once they are assembled by the code. But this is chemical engineers' work. In the next year or so, this will be fully automated, that the language model can do it automatically.
Okay. I saw many industrial collaborators sponsoring your research. Typical industrial interest is also saving costs, basically going for a lean. Do you see potential there? Because you said we do now, for example, this automated anomaly detection. Do you see that as a way to have less operators, or how do you see this used in practice?
Yeah, it's not a question about saving firing people. It's more a question of how to put it. Even if you are a large company, you may have one or two very highly qualified process reaction engineers, but you have way more problems for them than you have people to solve them. So this kind of tool allows to pretty much upskill other people so that they can do similar tasks. And so the very highly qualified reaction engineers will have less time to spend on each individual sub-project. So you can do more advanced tasks by many more people compared to what you can do today. It's more of almost like democratizing very, very difficult tasks. So it's not about firing people, it's more about empowering people, I would say.
Okay.
That's the real target. And the other target for our industrial collaborator is management of in-house knowledge. Because once they've gone through the process of including the existing models into this environment, that stays, and they can always look it back again, and they always know when did they do what, by whom. So this environment has a lot of metadata, and so all of the analytics which you can do with language models is then becomes available. If those previous tasks were not in this kind of environment, then you can't do it. They're dead pretty much. So we can't access them.
Okay. Many questions still in the chat, but I will select one of them. So in chemical process modeling, top-down data-driven approaches often struggle with when experimental data is limited or not representative, while bottom-up models require many kinetic parameters and constants that can introduce large uncertainties. How do you overcome these limitations in practice to build reliable AI models for chemical processes?
Yeah, I mean, these are understood problems. Yeah, you always have model identifiability, state variables you can't observe. I mean, there is not a magic bullet to those problems. There are plenty of codes to help with this in terms of either in terms of design of experiments to guide the generation of data. You link it with automated labs, and then it's much easier to solve the bottom-up problem. There are AI codes which are trying to figure out what's the reality based on correlations and so on, statistical correlations within data. So I think AI helps on different fronts, but this technology is there to combine the statistical AI tools and language model type tools with the fundamental knowledge, so that overall approach is more effective, I would say. So this is not a magic bullet. This is part of the overall solution.
Okay, but that's very nice answer. I want to thank you again, Alexei, for this great talk, and I will hand over the word to Georgios for introducing the next speaker.
Thank you very much, Kevin. Thanks, Alexei. Very interesting talk. I have some questions myself, but we have to give priority to the audience. Maybe we can take them offline. So let's move on with the second speaker. Our second speaker is Professor Idelfonso Besados Reis Nogueira. Correct, Idelfonso? Good. Okay, from the Norwegian University of Science and Technology, NTNU. Idelfonso's research focuses on the integration of artificial intelligence, process systems engineering, digital twins, and optimization for chemical industrial processes, with emphasis on hybrid and interpretable AI approaches for process modeling, monitoring, and control. Today, Idelfonso will talk on a topic that, in my opinion, complements the previous talk. We will focus on domain-informed AI and chemical engineering. And I have to also say that Idelfonso was recently asked by EFCE to coordinate a new section on AI for chemical engineering. And I'm personally looking forward to collaborating with him in this role as chair of the working party on processification. So Idelfonso, the floor is yours.
Thank you very much, Georgios. Thank you very much, everyone, for being here with us today. And it's a pleasure for me to be here with you talking about domain-informed AI for chemical engineering. And the main goal of my presentation is to highlight how important it is for chemical engineers to join the AI development community and contribute with our expertise and our experiences. So moving forward, the next slide I have for you, and I seem that I have a problem with moving the slides, so I have to stop sharing my screen for a second and start sharing again for a few seconds. And here we go. Okay, so before we start, I'd like to bring a small analogy. And usually when I talk about domain-informed AI, I like just to introduce what I mean by domain-informed AI using this analogy. So I think that we are all familiar with the learning process, and mostly while the child is learning a language, we are overflowing the child's brain with words, sentence, and so on and so forth. And the child will start to learn based on the partner. The child will be recognized behind the words. And if you look at the partner, the general, and the standard partner, the past tense for the verb to go is gold, just based on the partner and the data presented to the child. And the child will start to repeat, will start to conjugate the verbs in the past tense by adding ed termination, and based on the data, only the data, this seems reasonable. But after a while, the child goes to school and the expertise will come in. So the child will have contact with the grammar, with the language structured and systematized into roles. And those roles will help the child to learn the grammar and the syntax. And the speech becomes more precise, generalizable to new situations, and transferable as well to new situations. So the rules refine the raw creativity into structured mastery. And this, in this sense, is a little bit how I see what is domain-informed AI, is ground data with expert knowledge. As I have the example here for the child, we can do that for many different applications. And we should not only rely on data, because the data is presented to us a statistical approximation of the reality, but mostly always as chemical engineers or with very specific expertises. Sometimes we need to address also the exceptions to the rules, and we need to translate the exception to the rules in terms of machine-readable information. And how we can do that? First of all, we as chemical engineers, we speak the grammar of systems in general. We know the laws, the constraints, and the mechanisms that govern the physical systems. We know how molecules are interacting with each other. We know how to convert a raw material into product, and we can teach AI how to reason, not just to mimic partner in the data, but also how to attain the reasoning and the physical knowledge we have built throughout the history of chemical engineering or the history of other applications expert systems. So it's not only about replacing data, but it's about grounding the data with our knowledge. And this is a little bit how I see the domain-informed AI. And domain knowledge can help AI to generalize, extrapolate, and behave reliable in real-world applications. And mostly when you go to industrial scenarios, this is very essential. So what is domain-informed AI? In other words, instead of brute force learning from data alone, we embed scientific knowledge directly into AI architectures. The results, the model can reliably integrate with physical meaning, with physical consistent. And today I would like to walk you through those ideas from a single property model to a foundation model. And it can even show the potentials for a chemical engineer to build a foundation model, but we can do that. And I will show you today that we, as chemical engineers, we can also contribute to the field of AI architectures. We can build foundation models, and we can bring also on the other way of the road our knowledge to the field of computer science and AI development. So first of all, I would like to think a little bit with you about how we can transfer our knowledge into a molecular model to predict a given property. So we know there is an implicit relationship between, for example, the boiling point and the vapor pressure. And we know, for instance, if you're in a scenario, we might have a lot of data for boiling point, but we might not have much data for vapor pressure. So we can, first of all, transmit this information through tools such as transfer learning. So we can pre-build a graph neural network to predict the boiling point, and we can form embedding space, so a latent space with information establishing the relationship between molecular structure and boiling point. And inside of this latent space, we know that there is the implicit relationship between boiling point and vapor pressure, and we can leverage that. And this is a knowledge that we are bringing with us from our understanding of chemistry, thermodynamics, and so on. Furthermore, we know that inside of the molecular representation of a molecule itself, there is chemistry implicitly in that molecular representation. And we can make use of molecular descriptors to represent a molecule, and we can transmit this information to a machine into a machine readable format, to a machine learning model. So the model can also be constrained by the knowledge inside of molecular structure. So this is another way also to transmit this information. And for that, we have tools very well known in the literature nowadays, for example, graph neural network that can look at a graph, and the graph can be a representation of a molecule, represented in edges and the nodes, so how each atom is connected to each other. And you can transfer that, you can convert that into machine readable format, and you can inject that into a model. And the model can predict our boiling point. We will form the latent space, as I explained to you. And we can transfer then this latent space, this vectorial representation of the relationship between molecule and boiling point, into another model, which will finally predict our target property, in this case here, the vapor pressure. So we have done that, and we saw that by doing this, we could improve a lot the vapor pressure prediction. It's a simple case, but we couldn't achieve the results that we would like to do. So we wanted to have vapor pressure prediction as a temperature-dependent variable, and we want to have these for any type of molecule present to the model, not only molecules, that we have already the experimental results available. So what we have done, we did a step further. So we start to think how we can change a little bit the AI architecture that we're using here. In this case, a simple density beautiful neural network. And we start to change a little bit the shape of the activation functions inside of the neural network in a way that they could represent the mathematical functional forms known from thermodynamics. In this way, we use the Antoine equation, which is a very well-known equation from thermodynamics, to predict vapor pressure. And we use the mathematical functional form, not Antoine's equation, but the mathematical functional form represented by Antoine's equation. And we could constrain the output of this model, and we could extend significantly the capacity of this model to predict vapor pressure. So I just wanted to introduce here how we can transfer knowledge from our field into AI model. And we have done so, and we did a step further. We expanded this idea to other molecular properties. For example, the X-spoofing model that we developed to predict the viscosity. And behind this model, we have the same concepts as I already explained to you to predict our viscosity as a temperature-dependent variable for any type of molecule we present to the model. And I would like to share with you a little bit the results we have. If you are interested in reading a little bit more about this publication, please feel free to check our paper. But what is very interesting here is to look at the interpolation scenario. So we have a series of experimental points from 0 to 100 Celsius for our viscosity for those two molecules I have here right now. So if you have a look at my first set of molecules for the interpolation scenario, the baseline model, which is a model without the domain constraint inside of the model, starts to shake, to oscillate a little bit between experimental observations. And this is a scenario not so well explored in the literature. When you think while you are modeling a system, you trust on the interpolation of a model, and we analyze usually the extrapolability of this model. But the baseline model here shows us that we should be also careful between experimental observations. We should be careful and analyze how our model behaves there. And within the trained dataset, within the validation dataset, we can see already that if we have a new observation within the train range, but not close to the points, the experimental points we have, the model will oscillate. And here you can see clearly the oscillation of the model, and usually we don't analyze this while we identify the model because we are using the trained dataset, the validation dataset, to identify our structure. And on the other hand, the model with the domain information constraining its output, it behaves well because it has a mathematical functional form filtering its output, making sure that the model is behaving in line with what we expect. So this is good. We could see that our strategy is bringing more physical consistency, mathematical consistency to our prediction. But let's have a look now at the extrapolability. So what I mean by extrapolability, we are evaluating our model outside of the train area. So we have a data set between 0 and 100 degrees, and now we are predicting the viscosity beyond these limits, the limit of 100 degrees. And as you can see here, the baseline model, the data-driven model, starts to deviate, and it gets lost, completely lost after a while our domain-informed model could very well extrapolate our property. And this happened for the viscosity, this happened for the vapor pressure, and this happened for many other properties we evaluated along the way. So then after this, we start to think, okay, let's try to expand those ideas to the domain of foundation models, to the domain of large-scale AI models. You are nowadays very familiar with several different foundation models in the literature. For example, ChatGPT and the other commercial available solutions, they are foundation models for a specific domain. In the state of the art of foundation models for molecular representation, I have here for you 3 examples. The Geem beta 2, pre-trained with 77 millions of molecules using only smiles strings as input. The Unimol 2 scaled to 1.1 billion of parameters on 800 of millions of conformations, and the Molly self-supervised on 842 millions of molecular graphs. The key takeaway here is the fact that neither of those models can ensure thermodynamic consistency in its construction. It cannot directly incorporate temperature dependence or pressure dependence, and all those models, they are single modality, and they require separate fine-tuning models for each property we want to predict. So how we can bring the concepts we have been discussing till now, how we can infuse domain knowledge into the realm of large-scale AI models. We start to think the fact that a molecule can be represented not only by smiles, but we can use graphs, or we can use even 3D representation of the molecule. You know that the smiles is a 1D character sequence capturing the chemical grammar, long-range syntactic dependencies, and the substitute partners. But inside of the smile, we cannot represent, for example, geometry of the molecule. Then we can use graphs to represent the atoms nodes, as I already told you, the bonds as edge, and capture the topology, connectivity, ring systems, and functional groups. But there are limitations also in this type of representation. Then you can use also the 3D representation of the model. And you can see neither of those 2 last representations or neither of those 2 last modalities were used in any of those large models available in the literature nowadays. The Geem beta, Unimol, and Molly. So what we are to propose, we want to build a foundation model, bring all those modalities, because we know that the graph can capture the topological connectivity, but it cannot capture the 3D spatial arrangement and the molecular shape. We know that local chemical environments via message passing can be represented into graphs, but the static effects and the non-bounded interactions are not represented in the graph. So what we want to do, we want to build a foundation model that can build some sort of a big picture of a molecule, not only using smiles, but using graphs, 3D representations, together with the smiles. And together, these 3 modalities provide a complete structural picture, or close to a complete structural picture, the topology, the graphs, the syntax, the smiles, and the geometry, 3D representations, build up our comprehensive molecular identity. And this is very different already than the state-of-the-art foundation models for chemistry. And we start to think how we can fuse those 3 different modalities. Because they are very different modalities, they have very different ways to be represented in a completely readable language. So how we do that? First, the graphs, very straightforward. We have graph neural networks, for example, that can handle the graphs, as I already showed you. We know that the transformers architecture is very well known by handling sequence. So we can use them to represent the smiles. And we have pre-trained models for 3D conformers in the literature that we can also use to represent our 3D molecule, plus experimental conditions and molecular descriptors, which are important information to be provided to build this foundation model we want to build. First of all, after that, we start thinking, so we have different modalities. We can process those modalities by using those structures I just presented to you. But how we can fuse those modalities? And the fusing problem is a very interesting problem also, because you know that, for example, for isomers with the identical graph structure, they will, for the model will not recognize the difference if you are using only the graph. But if you use the 3D representation, this is a very important information to differentiate isomer with identical graph structure. But this is not valid for all the molecules. So how we can fuse all those modalities at the same time, we can learn when we should use more the 3D information than the smile, when we should use more the graph than the 3D, and so on and so forth. So for that, we built a structure based on cross-modal attention and gated diffusion, so we can learn in a self-supervised way which type of modality we should use for different type of molecules and different type of property predictions. And then we can unify this structure and add our predictors for the properties we want to predict. And this is the overall structure we have built. So we can build a foundation model for chemical property prediction based on chemical structure. And now I would like to guide you through step by step on this foundation model, the multipathing architecture. If you would like to read a little bit more, I invite you also to read our paper. But let me show you first the encoders. As explained to you, the molecule can be represented in different ways: graph, 3D, smiles, and here you have the encoders for each one of the modality we are using to represent the model. And of course, we need to have the experimental conditions for temperature, pressure, and also the molecular descriptors are encoded here in this first layer of our foundation architecture. And then the cross-modal attention-gated diffusion, we are fusing the information from these different modalities, as I have explained to you. So we are putting together smiles, 3D, and graph. And after that, we are fusing with the experimental condition and the descriptors and the learning when we should prioritize the 3D representation and we should prioritize other modality of data. After this, we have our fusion step, and fusing this information, building this whole picture, we can now project our latent space into the properties we want to predict. To do so, we have here the heads that we added to this model, each head handling a specific property we want to predict: solubility, log P, boiling point, vapor pressure, viscosity, and so on. And for each property, we went through the literature and we tried to find how we usually represent in terms of math, what are the correlations we are usually using in thermodynamics to represent those molecules, and we will start to constrain the output by using the mathematical functional forms available in thermodynamics. And then, of course, we need to train the structure, and we designed the loss function, prioritize the learning towards the latent space, and after that towards the properties. It was a two-stage training. We trained the backbone first, and then we freeze the backbone and train the heads. And we could do this in a very limited hardware if you compare to the hardware used to train the Chem Beta, for example. And we tried also to understand what is the minimum amount of data we need to achieve better prediction than state-of-the-art foundation model for chemical molecules. And this is the domain information we added to the heads, the mathematical functional forms represented, for example, by Andrade equation for viscosity, Van 't Hoff, Wagner, and so on. And the constraints also we are borrowing from thermodynamics and chemistry to constrain our model output. And by doing so, we could achieve a model that outperforms any model available nowadays in the literature for foundation models for chemistry. We compared here with Chem Beta, and with 2,000 times less data, we could achieve a performance outreaching, overperforming the Chem Beta for all the 9 molecules, all the 9 properties we want to predict. And this is an amazing result if you think that we are reducing significantly the computational effort to identify a foundation model. And not only that, we are reducing significantly the amount of data we need to build a foundation model by infusing domain information inside of the model structure. So for the vapor pressure, the domain formed heads also could make sure our model is predicting, as I told you already, producing a monotonic curve following the expected behavior, the same for the viscosity, the same for the heat capacity, and so on. So what we found out that Chem Beta cannot distinguish thermodynamic condition from smiley strings alone. It exhibits order of magnitude higher error for those properties we have here. And this is the final overview I have for you for the foundation model that we built. Our foundation model can fuse 3 different modalities of data while There is no other model available yet fusing such three different modalities to predict properties from molecular structure. And we also could achieve a foundation model that needs much less data. So multiple things, not the only model combining all the three structural modalities with domain-informed prediction head and multi-stack thermophysical prediction, but it's also a much compact model in a model that needs much less computational effort and resources to be identified. So the final takeaway I have for you here is that domain knowledge is essential, not optional. So if you want to develop efficiently models, use efficiently our resources available in terms of data and energy and so on and so forth, we should bring into the game our knowledge, our expertises. So multimodal representations can capture complementary information. So let's use different ways to represent the same information. Chemical engineers are uniquely positioned for this to shape AI world by bringing our knowledge. So first of all, thank you very much for the invitation to be here today. I'll be happy to discuss with you. You can reach us out by email, by LinkedIn, or whatever is easy for you, and I'll be happy also to answer your questions. And we have also a small survey running around to understand the AI landscape within the EFCE community. Please, we have here the QR code for you if you are available to answer 2 minutes survey addressing the topics we are discussing here today. Thank you very much.
Thank you very much, Idelfonso. There is one question in the Q&A box. The question is whether you can use this approach, I guess a multipathing approach with polymers to predict properties.
Yes, it's scalable, the approach, as long as we understand, as we have done the exercise for how to represent the molecules, what are the important ways and modalities of data available for us to represent the polymers. As long as we systematize this, it's feasible and scalable for other systems in large molecules.
Okay. There is one more I see. The question is, isn't choosing a functional form for a property make you fall directly to same deficiencies of that formula, thus limiting the possible predictive abilities of the AI models?
Indeed. We are limited for that functional form, and this is one of the issues we handle in the multiple thing approach, because in the head we have several different functional forms we are using to predict that given property. So we are evaluating the epistemic uncertainty behind the mathematical functional forms available to represent that property. So we are not limited to only one, but we are listing several possibilities, and we are using all of them to build the epistemic uncertainty evaluation.
Okay, thanks. Well, I see Kevin eagerly waiting to take the word, but still, I would like you to comment on one more thing. This approach has been, if I understand well, has been applied so far to predict properties. I'm wondering whether it's been applied to predict or optimize processes, not only properties.
And that's a next step, Georgios. We have ongoing works in the direction of fault detection, diagnosis, and the dynamic series time series. And I'm sure that in the near future we can do that also to optimize and design processes.
Okay. Many thanks, Idelfonso.
Thank you very much.
Kevin, the word is back to you.
Okay, thank you, Georgios. So it's my great pleasure to introduce Professor Artur Schweidtmann. He's an assistant professor of chemical engineering at TU Delft, where he leads the process intelligence research group focused on AI, machine learning, and process systems engineering for chemical applications. His research developed advanced algorithms for robotic chemistry, process optimization, surrogate modeling, and molecular property prediction. He holds a master and a PhD degree from Aachen University, complemented by research stays at Carnegie Mellon and the University of Cambridge. Professor Schweidtmann, the floor is yours.
Perfect. Yeah, thanks a lot for the kind introduction, kind invitation. It's a great pleasure to be here and also to talk alongside Alexei, Idelfonso, and Enis today. I'd like to talk about a topic that we relatively recently started to work on in our research group, which is about agentic AI for next generation of chemical process design. And this work has been mainly driven by my PhD student, Sophia Ruprecht, as well as Qinghe Gao, with support from Giacomo and Maximilian. And I'd like to start by pointing out the obvious, which is the rise of Gen AI in academia and industry. So over the last few years, we have seen more and more Gen AI use. Gen AI learns essentially patterns and structures from large data set, and it's able to generate new content that's consistent with the learned patterns or data distributions. And in particular, we see a lot of use of large language models, which is a subset of Gen AI trained on large text corpora. But we also know that Gen AI is not limited to text. There's also other data modalities, in particular images and videos, where models have been developed and are also commercially available. If we look at the chemical engineering domain, we see also that Gen AI is actively being researched and used across all the scales. So we see a lot of interest on molecular design, so generation of new molecules, maybe with optimized or targeted properties. This is already ongoing for a long time. Likewise in retrosynthesis, reaction pathway generation, and so on. And then more recently, we see Gen AI in process synthesis, in the engineering and control, supply chain prediction, and also in education. And indeed, our research group has also contributed a lot, especially on the process synthesis and process engineering levels here. But what you see in these works is most of them are monolithic end-to-end black box models. So what I mean by this is, let's take an example from our own research in process engineering, where we, for example, work on predicting PIN-IDs from PFDs. So piping instrumentation diagrams, generation essentially based on process flow sheets. In this monolithic end-to-end black box models, what we try to do is we try to learn this in one step. So one model is going to generate the whole PIN-ID flow sheet. Likewise, in molecular design, we see that a lot of these models take some kind of input, and then they try to generate a whole molecular structure in one step. And this is a promising approach, but there's also a few limitations to it. In particular, these approaches are prone to hallucinations and errors. So in the context of PIN-IDs, for example, you can imagine a PIN-ID is extremely complex. So if you look at a big chemical process flow sheet, a big PIN-ID, well, there's a lot of details you need to pay attention to. And you can easily mess up the whole flow by just making small errors here and there. So if you try to solve the problem in one step, you're prone to build in these small errors and you're prone to adding hallucinations. There's little explainability, traceability, because you try to do it in one step. And they require large and specialized data sets, which are often not available in this setup. And they don't have the ability to correct themselves or reflect on their own outputs. And this contradicts a bit with the workflows that we see in engineering today. So if we look at the actual engineering workflows, for example, in process design, we know that these are structured decision processes and not single predictions, right? So if we ask a chemical process engineer to design a chemical process, he or she is not going to, go to their office and in one step design the whole thing and return to you the ready PIN-ID. It's rather an iterative process. It spans multiple scales. We need to balance multiple objectives usually. We need to use specialized tools that include simulators, solvers, databases. There's heterogeneous data sources, like Idelfonso pointed out, different data representations we need to work with. And of course, there's the engineering constraints, the safety constraints, the physical constraints we need to satisfy. So the big question is Well, if engineering at the moment is not a single prediction step, how should an AI system be designed to actually support our current complex engineering workflows? And this is where the idea of multi-agent systems comes in. So multi-agent systems consist of multiple interacting agents that coordinate to achieve an individual or collective goal. Yeah. So this is a rather dry definition. So let me use an analogy between agents and engineers to explain in particular what large language model powered agents are, or agentic systems are. So what is an agent and what makes a great agent? I'm sure everyone has a good idea of what a good agent is. One example is James Bond. And if you look at it, James Bond as an agent is driven to solve a goal or an objective. And that's to stop a criminal mastermind threatening some kind of global security problem, right? And then the agent has also access to a number of tools that might be a nice car, secure communication, and so on. And if we take this idea of an agent working to solve a goal with tools in the chemical engineering domain, well, I think we're all good agents, right? So we also have our goals. Maybe we want to optimize a chemical separation process to improve efficiency. And we also use tools in order to achieve our goals. So that could be process simulators, chemical property databases, or engineering documentation. And if we talk about multi-agent system or agentic AI, there's not only human agents, there's also the AI component. So what is an AI agent? Well, an AI agent could be represented through large language model, could be represented to small large language models that are trained on, our domain or specific subdomains. These can also be rule-based systems or deterministic programs, like, for example, some kind of knowledge base that you query. Agents have a goal. In the context of large language models, usually defined through some kind of system prompt. And agents can also have access to tools through APIs, model context protocols. And through these, they can also access databases. They can execute code in coding environments. And they can also communicate with external APIs through the internet, for example. So now that we have an idea of what agents are, the question is, what is an agentic system? So this is basically putting many agents together and letting them work together to achieve a joint or individual goals, right? And we do that already in engineering, and we call it an engineering team. And that's based on human interaction. So it's teams that collaborate, iteratively negotiate, and jointly design, for example, chemical processes. And in multi-agent systems, we try to mimic this with a collaboration between human and AI agents, which can exchange messages, they can use tools, they can query databases and interact. And this is not completely new. This is actually technology that has been advanced in different fields and is also used already in practice. So one example in software engineering is a tool called Devin. So that's an autonomous agent system performing complex software engineering tasks. And it breaks down these tasks into planning task, writing and debugging computational code, running, executing programs, using development tools, for example, running unit tests or committing code to a Git environment, and iterating until the task is solved, right? And these tools you, in many cases, as a user, interact with through chat interfaces and through the artifacts that are being generated, so the code. An example is shown here, where the user wants to migrate a given code repository from one programming language to another. Right? Another example, a bit more close to our domain, is L Agente. which is a multi-agent system in the computational chemistry or quantum chemistry domain. Also here, we have a lot of agents that are organized by scientific expertise in a semi-hierarchical architecture, and also they share access to tools, including DFT calculations or Python tools. If we now look into the chemical engineering domain, so our domain, we see that there's also a number or a handful of multi-agent systems, mostly LLM supported, that have been recently developed and proposed in the scientific literature. Most of them also support some kind of tool calls. Some of them support human integration, and they're built on different frameworks. So the point here is that in our field, there are early works. They are promising, but still it's not broadly adopted. There's still not one big system that's being used. They are all specialized for some applications. So for example, some of these papers specifically target an agentic interaction between a user and a specific simulation environment like Aspen+, for example. So what we work on, what we propose is a multi-agent system for chemical engineering that is basically integrating across all the scales. And that is integrating also communication with humans. So we want the system to be human-centric and has access to our domain-specific tools, data, and modalities. So that can be on a molecular level, reaction networks, lab books, can be kinetic data, property data, design heuristics, sensor data, HAZOPs, PIN IDs, so all the engineering data, so where we work a lot on actually up to the economic, environmental, or global level, or supply chains, essentially. And what my PhD student is currently working on, Sophia and Chingre, is an initial research question, which is, can we design a multi-agent system that can support separation process design? And what she's been doing is she's following this procedure, which is, first of all, thinking about and designing a multi-agent system architecture. And this is largely inspired by what we as human engineers do at the moment. So what is a classical approach to solve these kind of problems? As part of this, identify relevant engineering tools and databases. So also here thinking about what's currently being used. What does an engineer need in order to solve this problem? Select agentic framework to implement this, implement the framework, evaluate the performance on actual case studies. So what I'm showing you today is work in progress. We are about to publish stuff soon, but it's still under investigation. So let's get started. What we start with is a hierarchical multi-agent architecture for separation process design. And this architecture we implemented in LangChain, which is an open source framework for agentic AI. And usually we start with a start node, which basically symbolizes a user interacting with the system. So a user starts to interact with the system by putting in a request, a written request usually, and that goes to a conversation manager. And the conversation manager has an idea of what's going on, what can I do, what does the system look like, and can negotiate between different agents in the system. And then what we did is we designed a number of expert agents, for example, selecting thermodynamic models, determining phases of a system, retrieving properties, chemical properties. What you can do as well is you can also design sub-networks. So you can have another sub-manager, in this case, a separation system sub-manager, which then again communicates with within its network. So here we have binary separation expert agents and multi-component separation expert agents. So what you see here is basically the manager-expert communication, but the agent can also communicate with one another. So for example, the multi-component separation agent might need chemical properties, And it doesn't need to go back to the manager to ask for that property. It can also directly, ask the other agent, the other expert. And in order for the experts to do their job, they also need access to tools and databases. And we always have a human in the loop as well when necessary, right? So the human can observe the whole conversation flow through the network, also needs to confirm external tool calls, and can correct the agents or interfere in the communication at any time, essentially. And after the problem is solved, well, that's the end node. That's where the conversation is being stopped by the conversation manager. What I want to do now is I want to go through these different agents and just explain a bit what's going on, right? So we have this manager agent. The goal of the manager agent is to coordinate specialized agents to solve the user's request. And the specific tasks include managing, moderating conversation flows, assigning tasks based on the specific agent's expertises, ask the human user for feedback or additional input when that is needed, formulate the final response to the user after all the internal communication is done, and also filter out of scope requests. So if we ask our system here to, write a poem for Mother's Day, well, the manager will reply right away, hey, this is out of scope. This is not our main expertise. Then we have the dynamic selection agent. The goal is to suggest suitable dynamic models for a given system. Also, in particular, we want to analyze the characteristics of the system, recommend a suitable model based on predefined rules. And we do that through a tool access. So we've implemented a Python-based rule inference algorithm here, and we've coupled that to a knowledge base based on, in this case, prior publication by Carlson. And what you see here on the right-hand side is just an example on how this decision tree, what's basically behind looks like, right? So we go through this decision tree step by step in order to recommend suitable thermodynamic models for a given system. Then we have a phase determination agent. The goal is to determine the phase equilibrium for a given system. So in particular, perform flash calculations, determine phase compositions and their fractions, handle pure multi-component mixtures, also support VLE or VLLE mixtures in our case. And how this is done is, well, we have an agent that is able to perform tool calls. In particular, we use the thermo package, which is a Python package for equilibrium calculations, essentially implemented in Python, and that supports some of the common thermodynamic property models, not all of them. Well, you see, for most of this, we need properties. So we also need to retrieve these properties, and we have an agent for that, which is basically the chemical property agents, or a number of agents, which is when we want to be precise. The goal of them is to retrieve relevant thermodynamic or thermophysical properties for both mixtures and pure components. So identify what properties are required, query databases, software packages in order to retrieve them. And our goal here is to retrieve over 30 relevant properties. And how we do it through a number of tools, tool calls, and different sources. So that includes thermo package again, includes databases like PubChem, NIST, and also if we don't find data in databases, the agent can also run machine learning models like this HANA or Grappa in order to predict pure component vapor pressures or activity coefficients, for example. And we also have a model or an agent with the goal to actually recommend suitable distillation-based separation methods. So the task is to analyze feed composition, separation requirements, evaluate potential constraints and operating conditions, and screen and rank conventional and intensified separation column configurations in this setup. And again, we have a heuristic system, basically a rule-based system that's based on recent literature by Lee et al. This is a contribution here from TU Delft from the group of Tony Kiss. And what's actually behind is first of all, an algorithm to retrieve information
about the system and the separation task. And then there exist Intensification decision metrics that Lee et al. Developed, which basically recommends whether certain separation columns are suitable or not suitable for a given task. So that includes conventional distillation, heat pump assisted distillation, heat integrated distillation, cyclic distillation, membrane assisted distillation, and so on. And this is again formulated as a tool call, integrated into the agent, so the agent can actually make a recommendation based on this engineering knowledge. Okay, let's look at 1-2 examples, case studies. We can start very simple by property retrieval. So what is the critical temperature and critical pressure of CO2? Well, we know for a fact the ground truth. And we have also benchmark, which is what happens if you ask ChatGPT out of the box, right? If you just go to the internet, go to ChatGPT and just ask ChatGPT, and you will figure out that, well, ChatGPT is actually correct in this case. You can also go through our multi-agent system, and our multi-agent system also delivers the correct answer. What's the difference? Well, ChatGPT is a large language model, essentially, so GPT 5.2 we create here, which essentially remembers these values from data, while in the multi-agent system, we have a tool call behind that's actually doing a database retrieval from this and also providing the source for this. But both provide the correct answer here. In the second case study, we want to determine the phases. So we have a given mixture, methane, ethane, nitrogen, with given concentrations at a given temperature and pressure. And we want to know how many phases are there and whether they're compositions. Again, we can do the flash calculations. We can calculate the ground truth. And we can also query this question to ChatGPT. And we see if you use the free online version, well, it gives you a relatively imprecise answer. And that's to be expected. If you, on the other hand, ask our system, what happens is the thermodynamic property models are actually selected, and the flash calculations are actually executed in the back. And then you get the actual result with sources on why this happened. All right, we have one more case study that I'd like to share, which is a bit more comprehensive one, where we have a binary mixture with given compositions, flow rates, and so on. And we have a target separation task, essentially, with given purities and overall recovery we want to achieve. And the task is that we want to select an optimal separation method to split this mixture. And what I share with you here is a video that shows basically the communication between the human and the multi-agent system, and also walks you through what's happening in the background in terms of the AI tool calls here. So let me run the video. This is just a user interface you see with a short introduction, README. And you can start to interact with the chat interface, checking, for example, with whom are you talking? Well, you talk to the conversation manager. This is to be expected because that was the first node you saw in the architecture as well. Then we here copy paste the query, the separation task that I showed you on the previous slide. And then it takes a bit of time. And let me stop the video for a second because it goes too quick otherwise. So what are we seeing here? What we see is switching to agent separation submanager agent. So basically what happens is the manager recognizes, hey, we're talking about a separation task here. So I should delegate this problem to the separation subnetwork and to its manager. And this manager is rephrasing the problem a bit. And then recognizing, hey, that's a binary problem, binary separation problem. So it's asking its expert agent for binary distillation, binary separation. And we can continue the video maybe.
What you see is here the conversation that the human can see, but that's basically conversation between the agents. The binary separation agent now recognizes that it needs physical properties for the components in order to proceed. And it's changing, basically asking the chemical property retrieval agent or expert. And this is now formulating a request for an external tool or database. And you can see here also the argument, so the JSON of the tool call. And the user needs to confirm that the tool should be called, because it can be an external call to website. So we wanted the user to basically confirm that. This is running, taking a bit of time for the first component. This is now the second component. See already it basically formulates a structured request that is then sent to an external API or multiple APIs here. You see already the cast number has been identified through PubChem, I believe. And we see here the results of the property retrieval. You see different sources. So from NIST, for example, with critical temperatures, critical pressures. We have information from thermal package, Flashpoint, PubChem. So different sources, the information from different sources is now aggregated here, essentially. That goes back to the binary separation agent. That is now calling its own tool. The tool is select binary separation method. And this is this heuristic support system for selection, basically, and for ranking different separation methods. This tool also gives you the result in a machine-readable format, a JSON format. And then let me stop the video here again. And you see the results here, which is shown here. Well, based on the research, based on the tools, this binary separation agent says, hey, this could be a cyclic distillation. HIDIC, I need to check, sorry, that's a heat integrated distillation. HPAD, that's abbreviation for heat pump assisted distillation, and conventional distillation, and gives you a score for those as well. And that's an internal score we calculate for recommending what's the most suitable method. Let me continue. And then this final information is given to the conversation manager, who returns that to the user again. All right. So what I've shown you today is that we build a separation, a multi-agent system supporting separation process design. The multi-agent system is traceable, transparent, and human integrated. However, it's work in progress. So we need additional tools, we need to expand the scope, and we particularly need to systematically validate the results. I believe we will see more of these multi-agent systems in chemical engineering, also for process design. But there is still a lot of research we need to do, and there are a lot of research questions we need to answer, some of which are around the architecture we need to choose. So it's unclear what's the best multi-agent architecture in order to solve our engineering problems. It's unclear how to best integrate engineering knowledge. There's a lot of works around it, but there's still a lot of research that we need to do. It's a bit unclear whether we will see chemical engineering foundation models like the one from Idelfonso, or if it will go more towards large language models. And of course, we need to work on transparency, safety, responsible development in order to deploy those models actually. With that, I'd like to thank you very much for your attention and happy to answer your questions.
Thanks a lot. We have a few questions here. So one of them is basically saying, I understand the role of each agent and the role of overall system, but how are the agents trained, constructed, validated?
Yeah, so it depends. So that's a question we need to answer and investigate for each agent individually. What you've seen, we showed today is most of these agents are not trained, not retrained. So most of these agents are based on existing large language models or small language models that are either accessed through public APIs or online APIs, or models that we can host on our own computers here locally. And then you specialize them through system prompts and by giving them access to specific tools like databases or Python packages or so. So in the setup that I showed you today, these agents are not fine-tuned or retrained for the specific task, but it's through prompting and enabling with tools essentially. But it doesn't say that, or doesn't mean that these agents cannot be trained. So you can train those agents, and you also don't need to rely on large language models only. You can have entire rule-based systems or deterministic algorithms behind the agents as well.
Did you find many cases where the agents gave very wrong answers?
Yes and no. So what we observe is that by breaking down the problem into smaller subproblems and having the agents communicate with one another, you overall have less hallucinations and issues compared to. So what's the benchmark? The benchmark is I have a complex engineering problem and I try to solve it in this one step, what I showed initially. And that's where we see really severe hallucinations, wrong results that basically create a lot of headache. By breaking it down, we have more traceable results and we can understand more what's actually going on. It's following our engineering approach. So it's usually easier for us to check as well.
Yeah.
But still, it's large language models. There are hallucinations. There are a lot of problems related to safety and reliability we still need to work on. So it's early stage research.
Okay. It's okay. Thanks. Considering the time, I want to thank you again for a very nice presentation and your insights. And I will hand over to Georgios again.
Thank you.
Yes, thank you, Kevin. Thanks, Artur. I think in your talk, some very interesting aspects of application of AI to PI were presented. And I believe that in our final talk today, Enis will bring the discussion even closer to processification. It's therefore my pleasure to introduce Professor Enis Leblebici from the Catholic University of Leuven. His research focuses on process intensification, scalable flow chemistry, and advanced process control, with a strong emphasis on integrating artificial intelligence and hybrid modeling approaches into intensified chemical processes. Enis is also a member of the EFCE working party on processification, and I'm particularly pleased to welcome him today. Enis will talk on mapping the AI journey in processification from prediction to generation. Enis, the floor is yours.
Okay. Thank you very much, Georgios, for the nice presentation, introduction. Thanks for everyone. It's a pleasure to be here and to present these amazing researchers. So today we are going to talk about three things, hopefully, if I have time: prediction, optimization, and generation in process intensification. So I'll go to the very beginning of the subject and I will discuss what of AI am I talking about. So AI has a lot of description, but I would like to focus on the first one, the simulation of human intelligence by machines. And here you can ask whose intelligence, whom we are replacing here. And I would like to also give a general family tree of AI and what I'm going to, where I live. I mostly live in this domain, in the machine learning branch and here in hybrid modeling world. But maybe if I have time, I'll just touch a little bit, not as much as Artur, to this point as well. So let's give our problem description, because if you are talking about hybrid modeling, you're actually addressing a problem in prediction. The situation today of a digital twin is as follows. You have a plant and you have continuous data transfer to and from this data, this plant in a digital domain. And here you have a model and you have a data, and you continuously running an optimizer to fit your model to the data. Let's focus on this model right now. In a plant operation, in a plant model, you have these, in a flow sheet model, you have these unit operations. Every unit operation has these nice equations. If you're a chemical engineer, you probably have learned or already using these equations in your daily life. Conservation, thermodynamics, transport equations, and reaction kinetics. These are great. These are the bread and butter of chemical engineering. They're general, transferable, and they don't require a lot of data. And they adhere to the physics. However, they have very low case specificness. So all the reactors of the same size, same mixing abilities are the same. You cannot have any quirks. So let's see how they work usually. Maybe you can relate. Let's focus on this scrubber, which is a continuous scrubber. You have your differential algebraic equations, a mathematical model. You put this model to a solver, and it will spit out this nice curve. It looks great, actually. Hooray. You start from 0, your concentration will come and will settle at a certain continuous dynamic balance. The problem is, when you put your experiments, you see something like this. If you have never lived this, please don't talk, because I'm going to be very, very jealous. But unfortunately, more than half of us chemical engineers, modeling people, will have this. This is called the reality gap. And of course, someone will be smiling at you. This guy, I will call him Jan. Of course, he's a artificially generated picture, but it's a very good representation of some people that will smile at our fancy equations. He doesn't care about those equations. He knows that Mr. Leblebici will overshoot the experimental data because he knows stuff that we do not know. And Jan is the guy I want to replace. I don't want him to lose his job, because actually we do not have enough Jans, because we don't, in Europe, human resources, high quality, high knowledge human resources are not a commodity. And we really need more Jans. And that's why we need more hybrid modeling, in my opinion. So what does Jan know? He knows all the inputs that we give to the mathematical model as well. And of course, he can estimate the output of this mathematical model with his gut feeling. But he knows other uncertainty inputs. Raw material producer, he knows when we get our petrol from X or Y, it's going to perform better or worse. He knows quality reports, he knows the operator name, meteorological conditions, season. He knows some things, he feels them. He has a gut feeling that knows, the model will be insufficient. So, unfortunately, we cannot give these inputs to our mathematical model. So we need Jan, but we don't want to keep needing him. So we need machine learning. This is where machine learning comes in. This is why we don't want only white box model, but a hybrid model. Okay, and together with Jan or the machine learning replacing Jan, we can actually fill in the reality gap. I talked about uncertainties. Let me give a very brief recap of uncertainties. We have the aleatoric uncertainties, and these are very prominent in crystallization, polymerization. These are irreducible variability coming from the nature of our system. We cannot make polymers of only one molecular weight. We will have a distribution of molecular weights. And the second thing is epistemic uncertainties. That means I do not know enough. This is Jan. So I don't know, as the engineer of the factory, I don't know enough. He knows things that I do not know. So actually, we should use the machine learning to close this reality gap, the deviation of this estimation of this prediction. So this is why will we need the reality gap, hybrid models. So I described the general case. How does these uncertainties come up in process intensification framework? In PI, we work a lot with weird structures, very complex structures, and alternative energy sources. So when we use, for example, photocatalysis or photo, activation, we don't know a lot of things. How the light will penetrate different structures, how the light what will be my light field. So already I start with a lot of epistemic uncertainty. And also, it is very difficult sometimes to estimate how the flow is going to be in interesting structures. So uncertainties actually are amplified in intensified systems. Furthermore, conventional processes have large hold-up and slow dynamics, and slow dynamics immediately will give you low output uncertainty. High G processes, very fast dynamics, very small hold up. This will, in many cases, increase our uncertainty. So let's do machine learning. Enis, you convinced us. Let's go for neural networks or whatever. So let's go. We have a plant. We have historical data. Let's say we hire a nice engineer who knows everything from polynomials to neural networks to support vector machines or whatever, and we make a data-driven model. We train this model, and we have inputs and process states. It is highly case-specific. A model will be valid for our process and our process only. If we go to the next door, it's not going to work. Domain knowledge not required. I can even fire all my chemical engineers and get software engineers maybe. And database description, okay, and fast computation, because once it's trained, for example, neural nets are very, very low computation cost things. But unfortunately, this will be a mistake, because if you go to pure machine learning many times, you will have prohibitively high data requirements. And we hear this all the time, high data requirements. So can you elaborate? Yes. A quality data will obey 5V rule. It will be high volume, so I will have a lot of data. I should have a lot of data. That's fine. In chemical engineering, we have now in a chemical plant, we have this sensors which spit out millions of data points per day. High variety of data. This is more difficult because chemical engineers are usually people who don't want to see any change. So every day, the same temperature, same pressure, same flow rate. So it is not always available. Velocity, the data should be recent. So usually it's okay. Veracity, low noise. The data, this is again, usually not there. And value. The information should come from where it matters, and this is 50-50. Sometimes there is vacuum and you cannot take samples. For example, I have seen low value data rather than high value data usually in chemical plants. So we have said also variety, and unfortunately, this is a good show of lack of variety. This is an ideal case on the left, and on the right, a distillation case. 80% of the output has unfortunately have 5% of the data. So this model will be, if you only rely on machine learning, this will be a very biased model. So let's bring the two worlds together. First principle models and data-driven models. When they come together, we have the hybrid models. They have lower data demand, high reliability because they are physics informed, and valorization of previous information is still possible. And we can put them, the data-driven in front or after the first principle model, a parallel system, or we can embed one to the other. Let's give a reaction case for the sake of our colleagues that have that come from reaction engineering background. So this is a real case by my former PhD student, Min Wu. You can see that we have a reversible reaction. A and B go to C, and C can go to go back. These are known and measurable chemicals, but we have also known and unmeasurable intermediates, and we also have unknown chemicals. And this is a real scheme that Min has done. We really had so many unknowns. So already unknown epistemic uncertainty, right? So what did we do? We have given composition, temperature, and purity a time series to a parallel system. So we had calculated to the best of our knowledge the first principle prediction, but we knew that this would be wrong. So the data-driven model was there. It was, I think, a rational function. It had learned already from the training that, oh, okay, this guy doesn't know a lot of things. I don't know what he doesn't know, but I can correct him because I have seen his mistakes within the historical data. So this is what we have done. And we have estimated the reaction rate. Of course, once we estimated the reaction rate, the rest of the predictions is completely algebraic differential equation sets. So we do not rely on data anymore. And this was the case. There were 4 reactors. 3 of them were temperature controlled, and 1 was just willy-nilly in the reactor room. And we had only 1 point for sample analysis. And very, very limited information. So what we did is we ran this training, and we have validated in many runs, and you can see that the mass percentage, the concentration composition could be estimated, and we even showed how it actually progresses. And we also have estimated the temperatures correctly. So you can say, Enis, okay, how much money did you make from this? Because you actually have solved a big problem for this company. We will come to that in the second pillar, optimization. So don't forget the reaction case. The second case that we have solved was solvent switch case. Was with Ulderico DiCaprio, now Dr. Ulderico DiCaprio, and was my former PhD student, a former postdoc, and now I'm proud of him. He's a collaborator of Artur Schweidtmann, and he's also a laureate of, is a fellow of MSCA, Marie Curie postdoc. So this is what we are solving is a solvent switch case. Solvent switch comes after reaction step and before crystallization step, where we switch the solvents. So you actually, it is a boiler. You boil away some solvent, and then you put another solvent while boiling the other solvent away. Both solvents away, actually. It is a big mush of uncertainties. We don't know a lot of things here. And for that, we have estimated with polynomial regressors the amount of the heat transfer and the liquid enthalpy. And we have solved the rest of the system, heat transfer like this, and the liquid enthalpy like that with black box remainders, and here the black box part is here. So we solved the equations, but we know that, again, just like Min, he solved the equations, he did his job as a chemical engineer, but he put a corrector, a tuner in the end of the equations, a black box part. So the ideal part is here and the black box part is here. So we also were quite successful here. You can see the most important thing that I would like to attract your attention was reboiler volume, and all the nice first principle white box models deviated particularly towards the end, and end is very important because in the end you should estimate when you actually have switched the solvents so that your process doesn't just go on for hours and hours. And all these models were deviating violently where we were quite well on point. So this was the case, and you will see how much money we made to the company in the optimization. So it's a very strong thing, hybrid model. You can put your mathematical model, you can correct your mathematical model with a known policy. So we said, can we actually make a method of making hybrid models and make an automatic hybrid model? And for that, we realized that we should take two decisions. One is which part of the model is deviating, and what is the most suitable equation to predict the deviation. Okay, I have to go faster because I see that my time is running. So one thing that we had to solve is uncertainty location problem. Where is the uncertainty? In this case, the uncertainty is going to be here. And again, there is a data quality problem. In some cases, the time series, we know all the systems, but some cases we have a missing variable. So we had to locate the uncertainty, we have to solve the data quality problem, and then we have to actually make an algorithm. And then we did, now it's recently published, we have done with Ulterico the SIND hybrid. So this works by actually looking at the time series and saying and finding an ideal how do you say, the dx over dt, so the time local variable for of this parameter, and actually putting a hybrid corrector for this variable. So basically finding what is deviating, and again automatically searching for this where the HXR is non-zero, and actually putting here a prediction H. And of course you can write it as an optimization system, and you can reduce your HXRs from unnecessary places, so your HXR will remain, your hybrid corrector is going to remain only where it is necessary. So it's a regularized system. So we have run a lot of use cases there. We knew this when we added unknown behavior to a case from the literature. And in just 6 training experiments, our hybrid model actually was correctly identified where we added this. Of course, we don't tell this to the hybrid model, this new uncertainty to the hybrid model, and it finds where it is, and it fits with reasonable accuracy. We have also changed the place again and changed the character of the deviation. It found the correct location and fit the hybrid model. We went to a different use case, which is bioreactors. We wrote our equations and added the unknown behavior to here. Again, the same thing happened. First principle model completely deviated while we were on point with the hybrid model. So yeah, the same thing. I want to go ahead. And Ulderico and I have worked on actually making a command line interface, a CLI, for automated hybrid modeling. And we have now a CLI interface software package called Hypro. And this we hope to connect it to an LLM like Artur. Maybe he can help us also to make Hypro even a chat assistant for hybrid modeling. Okay, so prediction, this is what we have done. Let's go to the optimization. Let's look back at our previous interesting cases. But here I want to show the family tree of optimization, and mostly I will be in this meta heuristics part of the optimization algorithms. So one thing that we have done is we used a reinforcement learning based control. This is basically you have an agent that is trying to learn the process and learn which action is good for within an operating space, and when he's or she's satisfied, it goes and gives the action to the real plant. I'm not going to talk about MPC, but let's focus on this. We used heuristic optimization, and for the reaction case, if they only allowed us to touch temperatures, we actually increased the productivity by 3.5%. When we were playing with temperatures and flow rates, when we were controlling it all ourselves, we actually increased 5.3% the productivity. For Ulderico solvent switch case, we used reinforcement learning, and overall there was 14.9% reduction in the costs of the process. So can we optimize other things? Can we optimize the structure for process intensification? Yeah. And if you define your problem, parameterize your geometry, and you can do experiments or do CFD simulations, then you can immediately do optimization if your CFD is light, or you can generate a lot of data with CFD and make a surrogate model and optimize. So this is something we have also observed and we have a review about this. I don't want to spend time about different parameterization strategies. I want to show what we have done in function-based parameterization. So basically, you can have functions that can give you very interesting geometries that you can use as intensified structures for reactors or separators. We worked with gyroids, which is which was most interesting for us for a photocatalytic system. So you can see that you can play with the gyroid structure by changing certain parameters. You can have more porous or less porous. So more porous to less porous with this, and you can change with XYZ, which will give you a different refinement in your structure. So we have actually designed the photochemical reactor. Now it's in review in Chemical Engineering Journal. You can see our photochemical space-time yield, and space-time yield was the most energy efficient with respect to other reactors. It was 7 times more energy efficient than the second best, and 100 times more energy efficient than most microreactors, and comparable space-time yields even as microreactors. So we actually have achieved the process intensification, let's say, mother load to replicate microreactor productivity with the but at larger reactor efficiencies. So I don't want to delve too much into generation because I don't have time. We wanted to make a specialized LLM. This is a study that we wanted to we did with Leuven AI Institute. So we wanted to make a process intensification LLM because normally it doesn't understand. A normal LLM doesn't understand from PI lingo or what we really want to do. So we tried the standard things. We actually did fine tuning. This is cheap to operate, fast to operate, and good for output formatting. But it was very expensive to build and can reduce the LLM's IQ. We actually made a very stupid LLM at a certain point. In RAG, I'm not going to go too much into detail. It is about we don't train the LLM, but we make a vector database for LLM to actually go and read about what we tell. This was better. Of course, it has a good reasoning, successful unification of terminology. It was cheap to start, but it's easy to data update, but it was expensive to run because you actually run multiple models at once. The chunking model to basically this thing is another model than the LLM. But then we actually made a very smart LLM that could speak PI. We have also experimented a lot with vibe coding, Claude anti-gravity codecs, but I'm not going to go too much into detail. It is all I'm saying. It is unbelievable what they can do it today, but unfortunately, because there is no time, I'm not going to go too much into detail. Conclusions: digital twins and white box model powerful, but not enough. Pure ML, there is a data limitation. Hybrid models are there, and we can do automatic hybrid models. And I would like to thank you very much for having me on board, and I'm open for questions. Thank you very much.
Yeah, thanks a lot, and it's a very interesting talk on mapping AI and PI. Since you work in both fields, I have an open question. I'd like your opinion on it. You touched a little bit upon it, but maybe you can elaborate on this aspect. As you know, the philosophy in processification is a little bit different compared to that in CRE. It goes beyond optimizing and improving a certain process, a certain reactive process. We like often to reconfigure a process design, to reinvent a process. For example, we like to combine functions into a piece of equipment. We like complex stuff. Yeah. So in this regard, I'm wondering whether AI can actually help discover new process intensification concepts, new processification technologies. For example, by automatically combining reaction separation, scanning, or exploring, let's say, unconventional reactor geometries and so on. How far can we go?
It is a question that goes to my heart. Thank you for this question. In principle, yes, because AI is basically replicating human intelligence, how we reason. And we have a lot of tools to reason, to generate new ideas and algorithms to do that. And my former colleagues that have just presented, they have proven this actually in multiple scales. Unfortunately, AI doesn't work without data. So we have to give hand in hand as a process intensification community, and we have to think about creating a framework for databases. If we actually have data, a very structured data that is encoded and machine readable, then it is very, very easy. Not very, I wouldn't like to say, but it is very, very possible. And I'm looking forward to actually taking part in any effort that would give this proud project a hand.
Mm-hmm. Yeah,
So
thank you.
Data is the thing. We need to have data.
Mm-hmm. Another issue frequently encountered in the field of processification concerns scalability. Because of the fact that most of the PI technologies are quite complex and emerging to a large extent, scalability is challenging. I'm wondering whether AI, in your opinion, can reduce the uncertainty of the upscaling process using mostly lab or pilot scale data to come up with a more reliable upscaling process.
Yes, we can do that. Alexei and again, all of us have basically touched on it. If you can make your designs machine readable, such as Alexei's first symbolic strategy or puffins of Idelfonso, we can actually make a model learn from former data of how it scales, and then we can actually estimate the uncertainty, aleatoric uncertainty even, of different scales of the same design. So this is a very interesting question, and I think it's an active research area. We are all looking into this. So there is another way AI can help, because computational fluid dynamics of mixing, for example, it is still, as of today, particularly after the RAM crisis, it is very, very computationally expensive. Data-driven CFD is real, and it's cutting down computational fluid dynamic costs significantly. So if we can make a database, and if we could make CFD cheaper, computationally cheaper, it would actually make a revolution in scale-up, because we would have less epistemic uncertainty for different scales.
Okay. Many thanks. Excellent presentation. It's already a little bit late. It's already past 5:15. So if there are no further comments, I think we can start closing the webinar. From my side, I would like to thank again all the speakers for the excellent presentations. I think today we saw many complementary AI perspectives in the field of chemical engineering. I'd like to thank the audience for the participation. Several questions were asked and answered. And of course, thank again Martin and Jarka and Bulo for supporting the organization of this webinar. Kevin, I don't know whether you want to add anything?
No, thanks a lot, everybody. Great talks. So we look forward to the next one, I think, maybe next year again.
Great. We wish you all a very good evening then.
Thank you, everybody. Really good webinar.
Enjoy your weekend.
Cheers.
Bye.
Bye. Bye.
Good weekend.
Bye.
Bye.
Thank you, Jess and Martin. Yeah.